Good morning and welcome to this the 24th lecture of the course Stochastic Hydrology. In the last class, that is the lecture number 23, we essentially discussed the Markov chains, and previous class to that we introduced the Markov chains, the transition probabilities, and then we also discussed steady state Markov chains and understood how to derive the steady state probabilities of a Markov chain. Then in the previous lecture we also discussed a few examples on Markov chains. So far the journey has been on discussing the fundamentals of stochastic processes with a few applications through numerical examples and so on. For example, we also discussed in earlier classes the probability distributions, the joint probabilities, conditional probabilities, and then data generation, data forecasting, analysis in the frequency domain, spectral analysis, and then the time series analysis, where we discussed in detail the ARMA type of models and then their applications to data generation, hydrologic data generation as well as hydrologic forecasting. Now onwards, the focus of the course will slightly shift in the sense that we will take up specific applications of many of these techniques that we have learnt for various problems that we encounter in hydrology, be it the flood forecasting or determination of design storms or run lengths of drought analysis and so forth. So, now onwards we will specifically pick up a few topics of direct application relevance to hydrology and then discuss how we use the theory that we have learned so far on their applications, on the applications that we would be interested in. Now, some of these may have been covered also in your applied hydrology course or the basic hydrology course. For example, we may start with flood frequency analysis today, which may have been covered in your basic hydrology course, but still because in as much as these topics use the theory that we have covered in the stochastic processes course, we will still cover even at the risk of repetition of some of these topics, so that the fundamentals of the theory that we have covered in their applications will be clear. We will start today with the frequency, with the topic of frequency analysis. Right at the outset, I would like to mention that we will be talking, as far as this course is concerned, of at site frequency analysis, in the sense that we are not talking about spatial distribution of the data or the regional frequency analysis, which is a different topic altogether, which is slightly advanced. But we will be discussing in today's class and maybe subsequent 2-3 classes, we will be discussing the frequency analysis of the data that is gathered at a particular location. This is called as at site frequency analysis. Say for example, we may have a rain gauge and we have been continuously recording the rainfall at a particular location. That type of data we will be using for frequency analysis, or the stream gauge data recorded at a particular stream location, a stream gauge location. What do we mean by frequency analysis? Most of the hydrologic problems are characterized by occurrences of extreme events. For example, we may be discussing about floods, which are really high extreme flows, or maybe we are interested in really low flows, which define either your hydrologic droughts or which may be critical for your water quality considerations. We may be interested in really high intensities of rainfall, which are necessary for design of stormwater drainage in a city, and so on and so forth. So, we will be interested really in the extreme values, either the high extremes or on the low extremes. So, for a while now we will depart from our normal processes and then focus on really the extreme processes. If you take any probability distribution that we have been seeing so far, let us say we look at some probability distribution like this, either a completely symmetrical or a non-symmetrical distribution. If you look at the extreme high values, let us say this is your random variable, the values that the random variable takes, and this is your f of x in our notation. There is a small tail here towards the right which describes the extreme values. The probabilities associated with these extreme values are all small. However, if you look at the distribution of these extremes themselves, either on this side or on this side, these distributions will have some interesting characteristics, and we will be interested in really looking at the distribution at the lower extreme or the higher extreme of the distribution of the parent population. This is called as the parent population. So, we are deriving the extreme values or the distributions of the extreme values from a given parent distribution. What I mean by that is, let us say your random variable x is your stream flows at a particular location. And we may be interested in particular values of stream flows, or we may be interested in the event that x is greater than or equal to a given value of x, let us say x 1 or some such thing, and we may be interested in probability of x being greater than or equal to x 1 for the flood flows. In which case we would be interested in getting the distributions of the really extreme flows which are derived from the parent distribution of the stream flow random variable x. So, we derive the extreme value distributions from a given parent distribution. In other words, the frequency analysis that we will be doing will be a function of, will be dependent on the parent distribution from which we are deriving the extreme value distributions. So, with that background, let us see what we really mean by frequency analysis and where it is useful. As I mentioned, we may be frequently encountering severe storms, floods, droughts, low water quality situations, high demand situations, and low flow situations, low rainfall situations, and so on. These are really extreme events in the sense that they do not normally occur. In fact, the more the severity of the event, the less frequent it is to occur. For example, we may be interested in the highest level of flood that can occur at a particular location. This may be least frequent compared to other events that we may be interested in at that location. So, the magnitude of an extreme event is inversely proportional to its frequency of occurrence. What do I mean by that? Let us say that we are interested in the magnitude of a flood which on an average occurs every 10 years. This magnitude will be smaller than a flood event that occurs once in about 100 years. So, as the frequency increases, the magnitude decreases. Once in 10 years is a higher frequency compared to once in 100 years, and therefore, the flood magnitude that may occur once in about 10 years will be smaller than the flood magnitude that may occur once in about 100 years. With this information in place, we carry out what is called as the frequency analysis. Now, the frequency analysis is a procedure of estimating the frequency or the probability of occurrence of extreme events. That is, we may be interested in answering the question, in how many years a flood of a given magnitude is likely to occur on an average, or what is the probability that in a given year a flood of a given magnitude will occur. These are the types of questions that we would be interested in answering through frequency analysis. So, the objective of the frequency analysis is to relate the magnitude of extreme events to the frequency of occurrences. Let us say a magnitude of 50,000 cubic meters per second of flood discharge. We would be interested in answering once in about how many years such an event may occur. So, that is how we relate the magnitude of the extreme events to the frequency of occurrence. By frequency of occurrence, I mean once in how many years the particular event is likely to occur. As I mentioned earlier, we will be doing the frequency analysis at a given site. This is different from the regional frequency analysis, where we may be interested in the frequencies of these events over a large region consisting of several data points. Let us say you may be interested in South India peninsular region, what kind of flood frequencies are likely to be present in that particular region. When we are doing that, we may consider the flow data from several streams, several stream gauges located in the entire region. So, that is the regional frequency analysis. But in this course, for the time being, we are focusing on at site frequency analysis, where we will be collecting data from a given stream gauge or given rain gauge, and then we will be carrying out the frequency analysis for that particular stream gauge or the rain gauge. A basic assumption in doing this frequency analysis is that the data that we have, let us say the stream flow data at a particular stream gauge, this is assumed to be stochastic, it is space independent and it is time independent. Now, for the same rain gauge, we are essentially looking at these two assumptions, namely that the data are independent and they are identically distributed. So, the data that you want to analyze for frequency analysis must satisfy these two conditions for the procedures that we are going to introduce now. This is called as IID. I also used this term earlier in the case of time series analysis. IID is independent and identically distributed. Now, how do we ensure independence? Let us say that we are looking at really high flows that have occurred in a year. Now, you may be gauging the data or you may be observing the data for every 15 minutes, let us say in a day, and you have a continuous monitoring of data for at the intervals of 15 minutes. So, you will have 4 such data per hour and 24 hours, and then in a year you will have 4 into 24 hours into 365 days. So, those many data points you will have in a given year. Now, if you put simply a threshold, let us say that flood values exceeding a certain amount, stream flow values exceeding a certain threshold value of stream flow, let us say 10,000 cusecs or some such thing. then in a given year you may have several such values which all exceed a given threshold of 10,000 cusecs. If you collect such values, they need not be really independent, they may not be independent. For example, a flood that occurs in a given year may have saturated the soil completely, and therefore, any rainfall that occurs subsequently may cause a flood of a high magnitude. Any high rainfall that occurs subsequently may cause a flood of high magnitude, and therefore, both of these floods that I am talking about may cross the threshold value that we have specified, and therefore, they are not independent events. However, if you choose the maximum value that has occurred, maximum flood that has occurred in a year, which means out of all these values that you collected, 4 values per hour into 24 hours per day into 365 days, those many values, and out of these values you pick up just one value, which is the highest value that has occurred in that particular year. Like this, for every year you have one value which is the maximum value that has occurred in that particular year. If you choose the annual maximum values, then these can be assumed to be reasonably assumed to be independent of each other. For example, in one year the maximum value may have occurred during July, in another year it may have occurred during October, and these two may not have any relationship at all, and therefore, they can be safely assumed to be independent of each other. And therefore, when we are choosing the data for the frequency analysis, it is important for us to choose that particular type of data for which the assumption of independence can be made reasonably. Then what do we mean by identical distribution? Remember, we are talking of the same random variable here. We are not talking about x and y being independent of each other. We are talking about, let us say, flow at a particular location, and therefore, we have a time series of flows. So, in that sense, identical distribution would mean time homogeneity. That means, you have a time series and then this should be homogeneous among time. Contrast this with space homogeneity, which we will talk about in regional frequency analysis. We are not interested in space homogeneity in as far as frequency analysis of at site data is concerned. We are talking about time homogeneity. So, we select that particular data such that the assumptions of independence and identical distributions are satisfied. These are the two most important assumptions that we make in frequency analysis. As I said, the assumption of independence is achieved by selecting the annual maximum or minimum of the variable being analyzed, as successive observations from year to year can be assumed to be independent. The assumption of identical distribution or time homogeneity is achieved by selecting observation from the same population. What I mean by that same population is that the data that you are analyzing must have come from the same watershed which has not gone through any drastic changes in recent years or during the period of the data. For example, sudden urbanization has not taken place, or the characteristics of the watershed have essentially remained unchanged during the period of the data. Then also the gauge that you have used for the data, they have not undergone any changes. For example, the type of gauge has not changed, or the gauge has not been shifted from one place to another place in the same watershed, and so on. So, you are looking at the same type of rain gauge, the same rain or stream gauge over the entire period of data, and the watershed has not undergone any specific changes during the period of data. This will ensure that the time homogeneity is maintained for the data. So, once we have ensured these, we will look at the purposes for which we use the frequency analysis results. As I mentioned, we would be getting answers to questions such as what is the return period or the average recurrence time that elapses between a critical event occurring in two successions occurring successively. Let us say that this year a flood of a given magnitude has occurred, then we will be interested in what is the probability that it will occur again next year, or we will be interested in the average time that may elapse between occurrence of this event successively. Does it occur once in 5 years, once in 10 years and so on. Now, these kind of questions are of extreme relevance, of high relevance in designs of dams, bridges, culverts and flood control devices and so on. When we build a dam, we may want to design it for a flood of a return period of 100 years. That means, you want to build a capacity, spillway capacity, which can pass the discharge which corresponds to a flood which returns once in about 100 years or once in about 200 years and so on. So, right at the design stage, you will make a decision on what is the type of flood discharge that you would like to pass through this particular spillway, and that discharge corresponds to your design decision of the return period. And the decision on the return period itself will depend on the type of designs that you are making. For example, for the dams, bridges, culverts, etc., you may be interested in 100-year return periods, whereas for the flood controlling devices, you may be interested in more frequent events, for example, once in 10 years, once in 15 years and so on. And when you come to urban flooding, your designs are based on much more frequent events and therefore, lesser discharges, smaller discharges. For example, urban stormwater drainage, we may be interested in return periods of once in 5 years, once in 10 years and so on. So, these are the return periods in the sense that the magnitudes of the discharges or the rainfall intensities that we are talking about will appear once in about those many years on an average. We may be also interested in drought frequency and magnitude. We may be talking about meteorologic drought or the hydrologic drought. Meteorologic droughts are related with rainfall essentially, and then the hydrologic droughts are related with the soil moisture and the water availability in terms of the stream flows and the reservoir levels and so on. So, we may be interested in the lower end of the distribution then. That means, the low stream flows, low rainfall and low soil moisture levels and so on. This will be useful in agricultural planning. So, the frequency analysis really provides useful information for planning either for the floods or for the droughts, and in most of the hydrologic designs we use the results provided by the frequency analysis. So, how do we go about this? I just talked about the return period. Let us go through the concept of return period more formally now. Let us say that we are interested in an extreme event which we define as the random variable, the event that the random variable x takes on a value greater than or equal to a threshold level x t. Random variable stream flow being greater than or equal to a value of 5000 cubic meters per second, discharge being greater than or equal to 5000 cubic meters per second. Now, that is the event that we call as an extreme event. That means, we put a threshold and then say that any time the threshold is crossed, we call that as an extreme event. Then we define the time between the occurrences of x greater than or equal to x t. That is, the event x greater than or equal to x t has occurred now, and then a time has elapsed and then again it occurs. Another time has elapsed and then again it occurs and so on. So, the elapsed time between two consecutive occurrences of x greater than or equal to x t is called as the recurrence interval, and we denote this as by tau. We denote the recurrence interval by tau. Then in a long period there may be several recurrences of this event. X greater than or equal to x t has occurred in, let us say, year number 1, it occurred again in year number 14, it occurred again in year number 15, occurred again in year number 29 and so on. So, the recurrence interval keeps on changing in a record of the time series. The expected value of tau denoted by E tau is therefore the average number of years in which the event x greater than or equal to x t returns. Let us say you had a record of 50 years and then you are interested in getting the event or the return period corresponding to an event x being greater than or equal to 5000 cusacks when we are talking about the discharge. And then in this 50 years of record, the average recurrence interval or the expected value of the recurrence interval may turn out to be, let us say, 10 years, and that is what we call it as the return period. So, expected value of tau is the return period t of the event x greater than or equal to x t. This concept of the return period is used to describe the likelihood of occurrences of extreme events. In fact, many times we confuse the concept of return period with the exact time at which the event occurs. For example, I may, when I say an event has a return period of 5 years, it does not mean that in the next 5 years it has to happen once, or let us say that 5-year return period event has occurred this year. It does not mean that that same 5-year return period event will not occur in the next year. In fact, every year has the same probability of this 5-year return period occurring, which will show it to be 1 by 5 in the subsequent slides. So, do not confuse the concept of return period with the time that it takes for that particular event to return exactly. It only indicates an average recurrence time, that means over a long period of time, on an average this event will return once in about so many years, which is the return period of the event. Let us say to drive home that point, we will take annual maximum discharge at a particular year for 45 years. So, from 1950 to 1994, 45 years are there, and the q that we are indicating here is the maximum discharge. That means, out of all the discharge values that you have collected over the year, you have picked up one value per year, that is the maximum discharge, and the units are q max, that is cubic meters per second. So, you have 45 such values. Let us say that we want to put a threshold of 1500. That means, we say that an extreme event has occurred whenever it has crossed a 1500 cubic meters per second. So, we draw the time series first. On the x axis you show the year and y axis is the discharge q. We draw the time series and then draw a line 1500 cusacks, q max, I am sorry, 1500 cubic meters per second. Any flow that exceeds this 1500 q max, we count it as a success in as far as our definition of extreme value is concerned. That means, whenever that event occurs, we count it as a success. Whenever it has not occurred, we count it as a failure. So, there are 9 such events as we can see here. from the data, whenever 1500, whenever the value 1500 has exceeded, we call it as a success. So, 1, 2, 3, 4, 5, 6, 7, 8 and 9. 9 times in the 45-year record, the value of 1500 has been exceeded. What do we do with this information? We will now calculate the recurrence interval. That means, in 1952 it occurred once. When did it occur next? It occurred next in 1956. So, there is a lapse of 4 years there. When did it occur next? It occurred in 57. So, there is a lapse of 1 year there, again a lapse of 1 year. So, this event of x being greater than or equal to 1500 had a recurrence interval of 4 years here, had a recurrence interval of 1 year here, recurrence interval of 1 year here, and then it again occurred in 61. So, 3 years and so on. So, this is what we count here. So, there is a recurrence interval of 4 years between 1952 to 56, then 1 year, 1 year, then 58 to 72. I am sorry, this was 1958, after that it occurred in 72. So, not in 61, it occurred in 72. So, there is a 14 years gap there. Then it again occurred after 4 years, 76. So, there is a 4 year gap here. So, we count the recurrence interval in years like this and then list it, which means what? In the record that we have seen, the recurrence interval is varying between 1 to 14 years. The event returned sometimes in 1 year, sometimes as frequently as in 1 year, as soon as in 1 year, and as distantly as 14 years. So, it varied between 1 to 14 years, and there are 8 such intervals, because we talked about 9 events and the intervals between them is 8 such intervals, and there is a 40-year period in this recurrence interval. So, what is the average recurrence interval? Average recurrence interval is in these 40 years 8 times it has 8 intervals are there. Therefore, the average recurrence interval is 40 divided by 8, which is 5 years. This is the average recurrence interval. This is 8 recurrence interval covering a period of 40 years between the first and the last occurrences. So, that is the idea of obtaining the recurrence interval. We leave out the first one, that is after the first one has occurred, how many times it has recurred and what is the average recurrence intervals, that is what we are talking about, and therefore, the average recurrence interval comes out to be 5 years. The return period of a given magnitude is defined as the average recurrence interval between events equaling or exceeding a specified magnitude. So, we specified a magnitude of 1500 cubic meters per second, and then we reckoned the recurrence intervals of such an event occurring. That means, x being greater than or equal to 1500, how frequently it occurred in the record. Having occurred once, how much time elapsed between its occurrence again, that is what is the recurrence interval, and then we computed the average recurrence interval. So, in the record of 45 years, the average recurrence interval turns out to be 5 years, and this 40 that we have used is the number of years between the first occurrence and the last occurrence. So, after the first occurrence has been noticed, we start counting the recurrence intervals. This average recurrence interval is in fact the return period of that particular event. So, for this example, the return period of the event that the flow magnitude equals or exceeds a magnitude of 1500 cubic meters per second, Qmax, is 5 years. which means once in about 5 years you can expect this particular magnitude to be equaled or exceeded. We will put this more formally through a probability now. So, this is the event that we are interested in, x being greater than or equal to x t. The subscript t here denotes the return period. As your return period changes, your x t changes, or as your flow magnitude here x t changes, the return period changes, and therefore, we denote this with a subscript of t, indicating that the flow here or the event here is dependent on the return period t. So, we will denote this probability p as probability that x is greater than or equal to x t. Then what we do, whenever this event has occurred, x being greater than or equal to x t in the record, whenever it has happened, we count it as a success. If that event has not happened, has not occurred, then we count it as a failure. So, any event x less than or equal to less than x t will be reckoned as a failure. Now, because we define p is equal to probability of x being greater than or equal to x t, the success occurs with the probability of p, then failure occurs with the probability of 1 minus p. So, the event x is greater than or equal to x t has a probability of p, the event x less than x t has a probability of 1 minus p. Because the events are all independent or the observations are all independent, the probability of a recurrence interval of duration tau. Now, what we are saying that once the event has occurred here, what is the probability that it occurs again only after tau years, because that is a concept of return period. What is the probability that it returns after tau years? What does that mean? That means that in the first year it does not occur, second year it does not occur, third year it does not occur, and so on, tau minus 1th year it does not occur, but the tauth year it occurs, that particular event occurs. And this probability is the probability that the event does not occur is 1 minus p, does not occur here is 1 minus p, etcetera, up to tau minus 1, and on the tauth year it occurs with a probability of p. Because the events are independent, the probability of such a sequence occurring is 1 minus p into 1 minus p into etcetera 1 minus p tau minus 1 times into p. So, that is what is the probability here. So, recurrence interval of duration tau is the product of probabilities of tau minus 1 failures up to this point, followed by a success in the tauth time period. So, that will be 1 minus p to the power tau minus 1 into p. So, this is the probability of the event recurring once in tau years. Now, we have defined the return period to be the expected value of the recurrence interval. Now, this is the probability of recurrence interval. The expected value of the recurrence interval is what we are interested in. So, let us recall how we define the expected value. Remember, we wrote expected value of a random variable when the variable is discrete. We wrote this as x p of x for I is equal to 1 to infinity. Same way, we are now defining it for the random variable tau, expected value of tau, the value of tau itself multiplied by the probability. So, this is the probability of occurrence, this is the probability. So, x into p of x, that gives the expected value. So, this is how we are getting the expected value of tau. if we expand the equation, that means tau is equal to 1, we put 1 into 1 minus p to the power 0 into p, that is p. Tau is equal to 2, we put 2 into 1 minus p to the power 2 minus 1, which is 1 into p, plus 3 into 1 minus p whole square into p, and so on. So, this is how we expand expected value of tau, and this we write it as p, you take it common, 1 plus 2 into 1 minus p plus 3 into 1 minus p whole square, and so on. So, this is the expected value of tau. Now, the terms within the bracket here, namely 1 plus 2 into 1 minus p plus 3 into 1 minus p whole square plus 4 into etcetera. Now, this can be equated to a series, that is the expression within the bracket. We can write this as this particular expression as 1 plus x to the power n is equal to, and this is expanded as 1 plus n x plus n into n minus 1 by 2 factorial x square plus etcetera, where we are putting x is equal to minus 1 minus p and n is equal to minus 2. So, in this if you put x is equal to minus 1 minus p and n is equal to minus 2, you can verify that you will get the same expression as it is in the bracket here. So, with this now what we are writing, for example, 1 plus x to the power n, the terms in the bracket. So, 1 minus x is minus 1 by minus p to the power n is minus 2, or we write it as expected value of tau is equal to p, that is this p divided by 1 minus p to the power 2, that will be p by p square, this becomes p square, and therefore, it is equal to 1 by p. And therefore, expected value of tau we are showing it as 1 by p, where recall that p is the probability of x being greater than or equal to x t, or the probability of a success. So, because expected value of the recurrence interval tau is in fact the return period, we write it as t is equal to 1 by p. Now, this is an important and very useful result, that is the return period is equal to 1 divided by probability of x being greater than or equal to x t, and mostly we write it the other way around, we write p is equal to 1 by t, that is the probability of occurrence of the event is equal to 1 divided by t. So, specify the return period, immediately you get the probability, and that probability we use for all our designs and so on. So, we are saying here the probability of occurrence of an event in any observation is the inverse of its return period, that is probability of x being greater than or equal to x t is equal to 1 by t. Therefore, the t year return period event is x is greater than or equal to x t, and it occurs on an average once in t years. Say for example, we look at this same example one that we considered, the same data 45 years data and the same threshold value 1500 years 1500 cubic meters per second, and we know that the return period of the event is 5 years. We just obtained that return period to be 5 years as I showed here. So, this is the average recurrence interval or the return period. So, this is 5 years. The return period is associated with a particular event. So, we are saying x is greater than or equal to 1500 qmax has a return period of 5 years. The event x greater than or equal to 1500 qmax has a return period of 5 years. Now, we will use that and answer the question, what is the probability that the annual maximum discharge in the river will exceed or equal 1500 qmax for the data in example 1. So, we simply put p is equal p of x greater than or equal to 1500, probability of x greater than or equal to 1500 is 1 by t, which is equal to 1 by 5, which is 0.2. So, this is how we obtain the probabilities for a given return period. Let us say our return period is 40, then obviously this 1500 will be different. As the return period increases, your magnitude also will increase. That is, a 40-year flood will be greater than a 5-year flood. A 100-year flood will be greater than a 40-year flood, and so on. So, this 1500 we had written as x t, which is associated with the return period t. So, from the return period you can obtain the probability. Now, related to this, an interesting and a useful question that we need to answer is, what is the probability that a t year return period event will occur at least once in n years? There is a subtle understanding that is necessary here. Let us say that we are designing a critical structure, let us say nuclear reactor or some such thing, and you want to protect this structure against flooding. And this nuclear reactor may last for let us say 1000 years or some such thing. And the flooding that you want to the flood discharge that you want to prevent it from may be a 1500 year flood or 2000 year flood and so on, or a PMF, probable maximum flood. So, we may fix the return period for the flood, which may be smaller than or may be higher than the time at which it is required, time for which it is required. So, we may be interested in getting the probability that in the lifespan of this particular structure that we are planning, what is the probability that a t year return period event will occur. To give another simpler example, let us say that you are building a dam and the dam is meant to last for 100 years, but the structure of the dam you may have designed for a 1000 year flood event, or the forces that correspond to 1000 year floods, which is different from the spillway discharge capacity. Spillway discharge capacity may be a 100 year flood capacity, but the structure itself may have been designed to withstand the forces that are caused by a 1000 year flood, the dynamic forces and so on. And therefore, you will be interested in answering the question, what is the probability that a 1000 year flood event will occur in the span of 100 year lifetime of the reservoir, and therefore, this question is relevant. What is the probability that a t year return period event will occur at least once in n years? So, let us try to answer this question. We will take the complementary event, that means at least once in n years. The complementary event to that is that it never occurs in the n year period. So, we will consider the complementary event that in n years the event x greater than or equal to x t does not occur at all. If it occurs even once, we are saying that it has occurred at least once, and therefore, if it should not occur at all for the event to be complementary. So, we first consider the event situation where the event x greater than or equal to x t does not occur at all in the n year period. What is the probability of this? That is, in the first year it does not occur, second year it does not occur, third year it does not occur, and so on. For all the n years this event does not occur. What is the probability that it does not occur in a given year? It is 1 minus p, because p is the probability that it occurs in a given year. And therefore, because the events are all independent, therefore, the probability that x greater than or equal to x t does not occur in any of the n years is 1 minus p into 1 minus p etcetera n times, because 1 minus p is the probability that in a year the event x greater than or equal to x t does not occur. So, this will be equal to 1 minus p to the power n. The event that the situation that it occurs at least 1 year once in the n year period is simply 1 minus this particular probability, that is 1 minus the probability that it does not occur in any of the n years. So, that will be 1 minus p to the power n. And what is p? P is the probability of x being greater than or equal to x t, which is simply equal to 1 by t, as we have seen. So, the required probability is 1 minus p to the power n, which is 1 minus 1 by t to the power n. So, this is the probability that a t year return period event occurs at least once in n years. And this is an important result, because we would be using these kind of results when we want to assess what is the risk that we are taking in building hydrologic structures, hydrologic designs. That is, we may have built it for 1000 year return period, but we would also be interested in getting the probability that 1000 year return period occurs in fact in the next 100 years, and that will give you a measure of the risk that you are taking in designing such a structure. So, we will use a simple example to drive home this point. Let us say we got the 5 year return period, that is the return period corresponding to a discharge of 1500 cumex is 5 years. We will answer the question, what is the probability that this 5 year return period occurs at least once in the next 5 years. Intuitively you may feel that this probability is 1, because you are saying that this is a return period of 5 years, and therefore, in the next 5 years it should occur at least once. But as you can see here, the probability is 1 minus 1 over t to the power n, and therefore, this turns out to be, this t is 5 years, return period is 5 years, and this is n. We are interested in answering the question at least once in the next 5 years, and therefore, this turns out to be 0.672. So, the fact that the return period is 5 years does not mean that it will occur at least once in the next 5 years. The probability that it will occur at least once in the next 5 years is 0.672. So, to summarize then, we have introduced the concept of frequency analysis, and we are talking about at station frequency analysis, in the sense that we are not concerned about the spatial or the regional frequency analysis here. We are talking about the frequency analysis with respect to a given data time series. The data that we use for frequency analysis should be independent and identically distributed. The requirement that they are identically distributed may be ensured by using the data from the same population, because we are talking about time homogeneity here. By same population, I mean the watershed should not be disturbed during the period of record, nor should the gauge, either the rain gauge or the stream gauge that you are interested in, be shifted or changed, or major changes have taken place in the way of recording of the data. The requirement of independence may be ensured by looking at annual maximum series or annual minimum series, where every year you pick up one value out of a large number of values that have been recorded, be it the maximum or the minimum. Then from year to year you can assume them to be independent. And then once we have the correct data, we do the frequency analysis. We introduce the concept of average recurrence interval. We call an event x greater than or equal to x t as an extreme event, and then we look at the recurrence or the time that elapses between occurrences, between consecutive occurrences of such events, and reckon it as a recurrence interval. we compute the average recurrence interval and then call it as the return period. So, the return period indicates that on an average such an event will occur once in about t years, where t is the recurrence interval, t is the return period. Then we also examined the relationship between the probability and the return period, and we showed that probability of x being greater than or equal to x t is in fact 1 by t, where t is the return period. Then we answered the question of what is the probability that in a given n year record the t year event will occur at least once, and that is a solution that we have obtained here. So, in the next class we will continue this discussion further and use the frequency factors to carry out the recurrence to carry out the frequency analysis. And we will also see how the frequency analysis is different or uses different values for different parent distributions. And as I mentioned right at the beginning of the class, the frequency analysis is dependent on how we define the extreme values, and these extreme values are in fact derived from a parent distribution. So, we are trying to look at the extreme value distributions which are derived from a given parent distribution. So, thank you for your attention. We will continue the discussion in the next class.